that I is equal to AR squared. Okay. And we know that R squared is the radius of gyration. So we can also see this in this form where you have P over A 1 plus by EC over R squared secant, okay, L over 2. And then we just replace with P over E A R squared. Okay. And then all we need to do is to take out the radius from the square root, radius of gyration, I mean. So secant L over 2R over square root P over EA. Okay. So both stress max, okay, you use either form, the answer will be absolutely the same. Okay. But the problem is this is you can make easy to make mistake. Okay. It's easy to make. Why? Because down here you formulate your PCR first. Okay, you can calculate your PCR first. Okay, over here you lump all of them in one expression. It can be difficult sometimes. Okay, so that is the theory of eccentric buckling. Okay, I'm going to do an example, and this example, if you need to get coffee, now is the time to get coffee. I'm serious. Okay, if you need to get coffee, now is a good time to get coffee. So the example that I'm going to do. Okay, so example number 1. So I'm going to, you should have this on your, on your avenue to learn. Okay. Right. So determine the maximum eccentric load P that the aluminum alloy can withstand without it either to buckle or yield. The ends of the strap are pinned. Okay, so it tells you that the ends are pinned. Okay, so what we know is the equivalent length is equal to L, right? Because it's pinned, because it is both ends, it tells us the ends are pinned, right? So we did this quite a lot. When it's pinned, what must we do? So we know that the LE is equal to 3 meters. Okay. Now you see the term buckle, okay, and you will see the term U. Okay, it will either it can support without causing it either to buckle or yield. Okay, the end of the straps are pinned. So why the different term? Okay, before I go any further, and I know that this is not given yet. Okay, note that for 2014 T6 aluminum, okay, the stress yield will be equal to 414 times 10 to the power 6 Pascal. Okay, that is our stress yield. Okay, now when they use the term buckle, I put the word when the term buckle is used. Okay, it is focused on centric buckling. Okay, so it's focused on centric buckling. So we know that centric buckling, we have PCR is equal to pi squared EI over L squared, right? And then we were to calculate a critical load or critical stress, which is equal to, before we calculate critical stress, there's no safety or factor over here. So i.e., I'm going to write this down. The factor of safety is equal to PCR over P, right? So in this context, the factor of safety is equal to 1, right? PCR is equal to P, right? But this is for centric buckling, and we later on have to calculate that the critical stress is equal to PCR divided by area, and we have to ensure that this is lower than our stress yield. Okay, right? That is our test, our criteria. Okay. Now, when the term yield is used, right, it is focused on eccentric buckling. Okay. Now, why do I say that? Why is it yield is focused on eccentric buckling? This is because, right, when we calculate eccentric buckling, we are calculating based on what? Stress. Yes or no? So we have this is equal to P over A 1 plus by EC over R squared. Secant, we have pi over 2 square root P over PCR. And then we have to ensure that the stress max is less than what? Stress yield. You see the difference now. Okay, you see the difference now. Okay, and this is important. I repeat again, this is critical. Okay, if you're not sure about this, then we're in trouble. But again, on this case, we know that PCR also equal to pi squared EI over L squared. Okay. Now the PCR for eccentric buckling and the PCR for centric buckling sometimes is not equal. It's not the same. Okay, I repeat again, sometimes it is not the same, and we have to be really, really careful. Are we clear? So these terms over here, very, very important. Okay, very, very important. Okay, right. So come back to this problem. Determine the maximum eccentric load. Okay. So I'm going to take this diagram. Okay. And I'm going to label this now. Okay, I'm going to label this. So over here, I'm going to label as in my transformation. So this is my X, Y, and then this is my rotation about Z. Okay. Then we have our cross-section view. All right, our cross-section view. So over here, this is my Y. Okay, and this direction over here, this is my Z. Right, and then we have our rotation about X. Okay, so let me draw it off. The transformation have to be correct and relate to one another. Okay. So now I'm going to now try to sketch this in 3D. Okay, I'm going to try to sketch this in 3D. Okay. So this is what we see in 3D. Okay. And then I were to draw my transformation. So on so my transformation, this is my X, right? So basically I've just rotated this. This is my Y, and using right hand rule. Okay, so X, hold on, X to Y, X to Y, right hand rule, and this is my Z. Okay. And then we have a load, and the load is applied. Okay, I'm going to the load is applied P. Okay, on both sides. So on the other side is also we have our P. Okay. So now we let's look at our XY plane. Okay. So let's now focus on XY plane. So before I go on our XY plane, did I write the U strength? Yep, I did write the U strength. And we did write the ends are both pin. Okay. So now we are going to look at the X, and this is our Y, and then we have rotation about Z. Okay. So this is focused on the XY plane. Or we can call this buckling. Okay, this term is also buckling about the ZZ axis. Okay. So when I sketch this, right, when I sketch this, right, we have the load. So let me draw the centroid first. We have the load over here. This is P, and this is P. And we know that this distance is our E, right? So in this context, we are aware that we have to apply, right? So